I'd like to welcome you all to this presentation, and I'd like to begin the formal part of the evening by welcoming you and acknowledging that I personally am standing on the lands of the Kaurna people of the Adelaide Plains. I acknowledge their deep cultural connection to their lands and the waters, and I acknowledge my respect for their leaders, past, present, and emerging. I am aware that we have people joining us from all over Australia, and that there are many Indigenous peoples throughout this great country of ours who each have their own deep cultural significant connections to the lands and waters of our country. Some housekeeping for tonight's presentation. Side conversations in the chat are perfectly okay. They're welcome. They are encouraged. Just, keep it respectful. If you have a specific question for either of our speakers, not somebody else in the chat, please put a few question marks after it and or before it to make it easier to find as we're going through the chat at the end. Questions will be answered at the end of the presentation so that we don't clog up the flow of the presentation. Additionally, please be aware that we are recording tonight's presentation, so you might want to keep your camera off if you've got anything in the background you don't want being recorded and possibly put up on YouTube or wherever. To follow on, first up, a little overview of the AIAA. We are the world's largest professional society dedicated to aerospace endeavors, with approximately 30,000 members in 91 countries. We are the world's leading aerospace publisher, publishing books, periodicals, journals, handbooks, and standards for design and manufacture. We are home to the leaders of today and of tomorrow. If you are not already a member of the AIAA, there are a number of membership types available. Professionals cost $125 annually, so that's approximately the same as Netflix. It does give you large discounts on journals, books, magazine subscriptions, and when we can all travel again, conference attendance as well. If you are a student, there is a student rate for $15 annually. Educators for K-12 educators is a free membership and access to a huge range of resources focused on aerospace. I'd like to apologize momentarily. These slides are a little bit old and have yet to be updated because there is a new membership type available starting this month, specifically aimed for high school students. If you know anyone who is a high school student who is keen on aeronautics, space, anything in those fields, they can have access to all of the resources online for the AIAA. Again, gratis, just like for the educators, free membership for high school students. There are a number of benefits to being an AIAA member. There you can access a global network of aerospace professionals, being able to discuss with leaders of your field, and perhaps being mentored by them if you are new to your career or to studying this field. Can access the largest archive of specialist aerospace publications held anywhere in the world, access numerous professional development opportunities, including continuing education courses and lectures, as well as getting daily news digests packed with global aerospace news, full of really, really cool things happening around the world. If you're curious, please, for more information, check out our corporate website, and those are the socials we have for the Adelaide chapter. I'd like to thank you all for your time and pass you on to Nimish, who will introduce our speakers for this evening's presentation. Thank you.
Thanks a lot, Barry. We do have two great speakers here today. And first, I would like to introduce Aude Vignelles, is the CTO of the Australian Space Agency. She has started her new role since last November, and to provide Australia and the agency the tools to implement the vision. So she has previously worked as the executive director for program and capability for the space agency, and was responsible for maintaining awareness of the state of the art for the Australian space industry, supporting her strategic and priority setting, and delivering on domestic and international activities. Her experience in leading companies is varied across both government and private sector as well. She has both background from ESA as well as leading the NBN as an executive manager for satellite and fixed wireless operations, as well as national manager for satellite operations. And we have today's second guest as well, Professor Phil Brand, who's the director at Curtin University for Space Science and Technology. He also heads the NASA Solar Exploration Virtual Institute, the Australia node, for the last 6 years. He also has a background from Imperial College London with a background in planetary sciences, and his papers with impacts and astronomical research center materials. Having said that, I will hand over the presentation to Aude herself to go through the slides ahead.
Thank you, Nimish, for the kind introduction. And I'm very happy and excited to be with you tonight to give you a bit of updates of where the agency is in terms of programs that we have set up 2 years ago now, how we are traveling against those. I think it's always good to see what we've achieved so far and what's to come. And after a brief update on all this, I'm looking forward as much as you are to listen to Phil, perseverance, ingenuity, Mars, and why we are going there. It's going to be fascinating to hear what Phil has to say about that. If you want to put the first slide up, Nimish, that'll be great. I always start with reminding what the purpose of the agency is. We are a young agency, 2 years. It's like we're starting to walk and run. So the next slide. And our purpose is really very clear, very ambitious. We want to triple the size of the industry in Australia, space industry, and we want to create 20,000 jobs. So that's the next slide, this one, thank you. Every day, when we have to decide which task we're gonna do when we have so many in front of us, we are asking ourselves, is this going to help me create jobs and grow the industry in Australia? And that's something that really drives us every day. Especially for you, the Sydney branch, there is a lot of happening in space, especially today. You may have heard that the SmartSat CRC has officially launched their node in New South Wales with the state government. And there's going to be a floor close to Vignelles in that building from the state government. That's going to be full of startups. That's going to be full of researchers, of industry, trying to develop the project that the SmartSat CRC is building, and I'm very looking forward to this. So I think we're going to start seeing a lot of pockets of initiatives in South Australia and Western Australia, New South Wales, Tasmania, and all that is going to build into the big strategy that we have to achieve this KPI. So 2021 is starting very well, and I think we're really into this delivery mode now. The next slide, the civil space priorities, is again a reminder of where we want to focus our energy and our effort. As you all know, space encompasses everything. You can think about any disciplines that exist in the world, there will be an application in space. So it can be very easy to disperse ourselves everywhere. We decided for the next 10 years to concentrate on these 7 areas of priorities. We have already progressed with the communication technology and services, the third on the top from left. We have published in December our technology roadmap. So one step is to identify the area where we want to grow and develop our capability. Next step, which is for us this year, the Office of the CTO responsibility is to deliver technology roadmap, really detailing the segments and the technology we want to grow and we want to be successful in. So communication technology and services, if you haven't seen that roadmap yet, please go to our website and download it. I think we have something like 700 downloads so far. We've done a webinar a couple of weeks ago. Publishing this roadmap has triggered a lot of interest nationally, but internationally, of doing projects now to deliver this focus segment. So have a look at it, and I'll be happy to go through that roadmap and do a specific session on this. The next roadmaps we're going to publish this year are the one on the right, space situational awareness. You all know how important that is to make sure we keep using space in a sustainable manner. Earth observation, that's quite obvious how much application is derived from space Earth observation. And you all know that we have done a pretty comprehensive study and report after the bushfire of last year, Christmas, how Earth observation can help managing, preventing and recovering from bushfire better. So the roadmap on this is gonna also be published today, this year, sorry. Robotics and automation. So that's something I know is very close to the heart of Phil. You have heard about the expertise that we have in Western Australia mainly, but all across Australia as well on remote operation. As you know, in Perth, that's where the like of Rio Tinto are monitoring and operating instruments and machinery that is 2,000 kilometers away in the Pilbara region, for example, hard to access, very harsh environment, can be cold, it can be hot, it can be very hard to access, as I said, and far. And when you look at the technology that has been developed to successfully and safely remote operate this machinery, it's obvious that we could export this into space. And you may have heard of this organization called AIAA, Australian Remote Operation in Space and Off Earth. That Curtin is part of this organization that is exactly looking into this. How can we export this expertise that we have developed over the last 40 years? So very well operational and track record demonstrated. How can we export that in space? And what we learn from space, how can we apply it on Earth? And of course, when you think about this, you think about the rovers and the robotics mission that are sent into far planets, so starting with the moon and then Mars, which is what we're talking about today. So I think Australia has a great future there to remote operate all this machinery that we really need to start developing before we can send people there. The other area, position, navigation and timing, is also a roadmap we're going to deliver this year. Access to space is also something we're going to start probably mid-year. And leapfrog R&D, this is a bucket where we know there is a lot of capability in Australia that we have yet to discover. And the first one we discovered is space medicine and life science. We have so much to offer in providing support remotely to human beings. And we'll start with Antarctic Division. You know that the Antarctic Division, these guys are cut from the rest of the world for 9 months during the year. All their need in terms of health and safety is again provided by the Antarctica Division that sits in Tasmania. So they have developed a lot of sensors, and they have a great knowledge of how psychologically, mentally, how do you cope with the isolation and so forth. So we are also working on developing a focus roadmap on that area. So progressing on this, we started delivering on the roadmap, and we should deliver the rest of it by the end of the year. The other thing we've been busy with, that's on the next slide, very briefly, the programs we have kicked off. You may remember that we've launched 2 programs, the Space Infrastructure Fund that we call SIF. Now, in space, you have to have acronym, otherwise you don't do space. And the other one is ISI, International Space Initiative. So all the Space Infrastructure Fund, but 2 have been awarded. So there was a competition for a grant, and most of them have been awarded. So we have a big data center in Perth that is offering big computing power to compute all the data you get from space, being from Earth observation, for space situational awareness, and everything we have yet to think of. So this is tickling along very well. In Perth, again, this robotic automation and AI command and control center. So Fugro was successful in that bid. They are building the first dedicated center to do remote operation in space. Ticking along very well too. I'm sure Phil can give us some updates if you want to ask more questions. In Adelaide, the mission control, so you're across that as well. Sabre Astronautics has won that grant, and they're almost completed their mission to build this mission control. They are going to do a lot of exercise around SSA, which is very interesting. When you come to Adelaide and go and visit this, there is a window so you can see all the activities that they are doing there. Tracking facility in Tasmania, so that's big antennas to track launch, to track satellites for SSA, and to track all the activities we may do in space. Space manufacturing facility, so a capability, sorry, so that's for the future Aerotropolis. We're trying to build an environment there that will trigger manufacturing of space components and satellite, why not? So this is in train. And the space payload qualification facility should also be announced. The successful grantee should be announced before the end of the financial year. Pathway to launch is the last one we have to look at. So delivering well. By the end of 2022, most of this infrastructure will be delivered. Total of all this is 20 million-ish. The next slide is just a summary of the international space investment that we have started as well shortly after we created the agency. So just as a reminder, Human Aerospace, they're delivering a skin suit. Akin is delivering AI for crew in space. Raytracer is developing virtual tools for astronauts to train underwater. Sabre also won a grant to deliver a mission operation software to help you developing your mission more efficiently. Silencium Defense in South Australia, passive radar for space situational awareness. Skycraft is developing a dispenser to deploy their constellation of spacecraft. Industrial Science Group in Sydney is developing a conjunction analysis tool to help you making decision when you see that your spacecraft is probably going to enter into a collision. University of Melbourne is doing the flagship of the ISI, so that's Spirit. It's a CubeSat that will be launched end of 2022-2023. University of Canberra is developing a motion sensor for helping the sickness you have in microgravity, and UNSW is developing a next generation of GNSS sensor. So all that is tickling along very well too for completion at the end of 2022 as well. And you can already see with this successful grantee, they are getting more attention internationally and nationally. They are growing, they're getting new contracts, and they're employing people. So that's exactly what we are trying to achieve here. And now we go to the surprise we had in October, not last year, but the year before last. So that's the next slide, when Megan Clark, then the head of the agency, and our deputy head, Anthony Murphy, went to the US with our Prime Minister, Scott Morrison. There was a big announcement of Scott Morrison giving the agency 150 million to contribute to the Artemis program that NASA embarked upon to move forward to the moon and beyond to Mars. So you probably have heard and probably attended the webinar what we described this Moon to Mars program that we are still developing for the last phase, but we are almost ready to announce successful grantee of the first part of this program. So you all across Artemis program, I won't go too much in this, but the next slide is just a reminder of how we've designed this Moon to Mars. And I think a good reminder of you that these grants are open to all, and I really invite you to look at the details of those. The first one, supply chain program, is a grant that is open constantly. So we're getting intake every 3 months. So if you're not successful in the first round, we can give you feedback and you can try again. And that's a kind of new way of doing things. Goal of supply chain is to tell to the whole Australian, if you're building a tech on the ground that needs to be qualified for space use, this is for you. This is to help you getting your TRL in space up and getting your product that is probably deployed for some application on Earth in space. So look at this. If you have a component, a subsystem, or a system that you think has an application in space, this is for you. The demonstration program has different phases. The first phase has closed, and we decided to fund phase A study. So I'm sure you're all familiar on the phases of space program. We start with phase 0, user requirement. Phase A, how are we going to fulfill these requirements? What's the size of the satellite? What's the power budget? What's the link budget, etc. Phase CD, you look at phase B, sorry, you start to think how to build it. Phase CD, you build, you launch, you operate, and then phase EF, end of the mission. So the demonstrator first phase is funding phase A. You all have great ideas of, I'm going to do this. This is the needs. These are the requirements. We're going to help you doing a phase A, very thorough, because sometimes you think, oh, with a CubeSat of 3U, I should be able to do that. And after you go through your phase A, you realize that it's not the 3U, you need this maybe 100-kilogram spacecraft. And this is really the cost. We want to help you really going through that feasibility study. What are we talking about in terms of mission? The next phase of demonstration program that will be open later this year is going to be, okay, now we need to fly some demonstration. We need to grow our track record in space in Australia, and that's what this is about. And then we have the Trailblazer program. So that's the big flagship, the big contribution that we want to do to Artemis. And we want to have a Australian flag somewhere. And what is this going to be? We've been talking with NASA a lot of looking into our capabilities. So we reviewed these 7 areas of priority I started with, and we tried to see what was the best match between the Artemis program and the capability we have. And we've come up with some options. We're going to present this option to the public. You're going to review that. You're going to tell us what you think. We're going to do a big consultation. And then we're going to take that on board and publish the guideline and say, okay, Australia, this is the Trailblazer. This is the mission we have all decided to do collectively. Now go ahead and bid for it. And without going too long on this, so this is Trailblazer on the moon, and I really hope that very soon we're going to start talking about mission to Mars and doing some space science, which is a subject close to the heart of Phil and mine as well. And I think that's a beautiful transition to you, Phil. Let's talk about Mars.
That was a beautiful transition. Thank you, Aude.
No
I'm going to just click share screen now. Hopefully that'll work. Thanks, Aude. Can everyone see that?
Yes, we can.
Yes.
Great. All right. So just really quick introduction. I'm Phil Bland. I'm Director of the Space Science and Technology Centre at Curtin. We're basically a group of planetary and space scientists and engineers, and we've got around about 50 staff and students in our centre. Oh, wait a minute. I'm trying to. Oh crap! There we go. I have to click it. We represent Australia's planetary science community to NASA via a tongue twister of an algorithm acronym, the Solar System Exploration Research Virtual Institute, which is NASA's program to basically try and connect space science, planetary science with human exploration. So an awful lot of what SURVEY does has to do with things like, the effect of dust on astronauts, volatiles on the moon, resources. I'm on a team at Ames, which is sending the Viper rover to the moon, looking for volatiles. So lots of fun things like that. Our research covers a lot of different areas of space and planetary science. We're also interested in space situational awareness and building our own small spacecraft. So as I go on here, what we'll do is we'll zoom in, obviously, quite quickly on Mars. We've been, me and my chums have been on a bunch of different missions, going all the way back to Cassini-Huygens. One of my colleagues, an engineer, actually worked on the surface science package for Cassini, for Huygens, sorry. My first mission was the Beagle 2 mission, which was a kind of a UK ESA Mars lander, and it was actually the first time that that people had really tried to use kind of almost forensic trace gas analysis to see if they could pick up signs of life without actually trying to look in detail at the rocks. Can you just use, you know, the presence in this case of methane to test for life? And that was what Beagle was built to do. It almost worked. It landed safely. It used landing bags as the Mars exploration rovers had done. And it almost worked. It was a real shame that whole landing systems worked. One of the panels didn't open, and that was why it failed, unfortunately. But it was a really cool idea. My PhD supervisor, Colin Pillinger, came up with that. Colleague of mine, Katerina Milchkovich, is on the InSight mission, which is a NASA mission studying the interior of Mars, the geophysics of Mars. And another colleague of mine was on Schiaparelli, which is part of ESA's ExoMars program. It's kind of an ExoMars Pathfinder. Unfortunately, its landing system didn't work quite as well as Perseverance did, and so we've still not had a good ESA success on Mars surface. ExoMars has been going a long time, so it'd be nice to see a success there. That's kind of a bit of a background on some of the mission stuff that that we've been involved in that relates to Mars. What I want to do is give you a sense, give folks here a sense of basically mostly about why Perseverance is going to Mars, why it's going to that spot, why it's doing some of the things it's doing in terms of the payload, the instruments that it's carrying, and what its main design job is built to do. So so there's a bit of a science background to this that I hope you'll stick with me for. When we're trying to get an age for planetary surfaces, and it's really important that we get ages for surfaces because that lets us basically build, it's one of the components of building a geological map. When we've never been there, all we've got to go on are remote sensing data, and fortunately there's an aspect of the solar system, the mechanics of how the solar system works, that lets us work out an age, and that is by counting craters. There's approximately a continual rate of impacts on planets in the inner solar system, so we can look at, so the more impacts you see on a surface, the older it is. This was actually first thought up in the early 60s. It was calibrated with Apollo, so you were able to look at the lunar mare, count the craters on the lunar mare. Apollo 11 brought back a sample of Tranquillitatis, and we could date that in the lab, and then you got a radiometric age that you could match to your crater count age. And after that, this is really what people had done. This is how we dated the surfaces of all asteroids and planets in the solar system, basically. Now, you'll be surprised to learn that, that since the early 60s, the method of counting those craters has been exactly the same. And that has involved a planetary scientist with a ruler just measuring the diameter and position of every crater that they can count on a planetary surface, which is really not very good under any circumstances, but starts to become completely untenable when you have, you know, the sort of resolution imagery that we can get now. The better resolution we have on a surface, the smaller craters we can see, which means potentially we could get, you know, just awesome age maps for with great resolution in age for planetary surfaces. Unfortunately, it's all been manual counting since the early 60s. Obviously, if we can think of a way of automating this, then that would be great. Colleagues of mine at Curtin, Professor Gretchen Benedicts and her team have spent 5 years developing a tool that allows us to do this. So it's basically a way of breaking down all the data that we have for a planet and automatically and working out both the number and position and diameter and degree of degradation of craters. This is one way of visualizing it. It's actually a lot more complicated than just counting round things. Otherwise, people would have done it a long time ago. To give you a feeling why this is so cool, so JPL can land Perseverance on Mars, but they can't count the craters at Jezero crater, which is where Perseverance is going. Gretchen can, and how cool is that? She's also my wife, by the way. So so that's an extra bit of spruiking there. So now that when we're plotting up this sort of data, we don't need to get into too many details of how we do it. We plot the numbers of craters as a size frequency distribution, and so you've got diameter along the bottom and then cumulative frequency on the y-axis there, and you fit that against what we call isochrons of kind of known crater number. So on this, we're counting, this is for Gusev crater, where Perseverance landed. And there's obviously been a lot of analyses of Gusev. In this, our ages using this automated approach are in black, and the literature ages are in red. So it's a pretty nice correspondence between those ones. And obviously the difference is some poor PhD student spent months and months and months getting the red ages, and we spent like a few minutes getting black ones. So now, as we're zooming in a little bit more on Perseverance and the why, the key aspect of Perseverance that sets it apart from everything else that has ever been sent to Mars is that it's a precursor to sample return from Mars to Earth. And why do we want sample return from Mars? It's fitted with a beautiful drill system, and there's a set of sterile tubes so that Perseverance is actually able, as we drive it around, to select spots where it wants to take a sample from, just like a geologist, cache those, and then those are going to be stored ready to be picked up by a second spacecraft that'll happen at some point, hopefully over the next decade, and return to Earth. And that's the critical difference that sets Perseverance apart. Now, what's a little bit different to Mars than for the Moon, when we went to the Moon, we didn't have any samples of the Moon when we went to the Moon, or at least we didn't think we did. We actually did, but that's a much longer story. Apollo brought back the first samples, and that let us work out how the Moon formed. In the case of Mars, we actually know that we have samples of Mars before we ever go there, and those are in the form of Martian meteorites. So in a sense, it's like free sample return. We already have free sample return from Mars. Now I'll explain why that sounds great. It's not as great as you might think. So this is a Martian meteorite. This became a very, very famous meteorite in the mid-late 90s when I was a young postdoc. So this is a Martian meteorite that was found in Antarctica at a place called Allen Hills, which is why it's got that ALH designation at the beginning. And it was found in 84, but it took a decade before people analyzed it in real detail. And what they did when they looked at that was they found, or they reported, features like this, and it became, you know, one of the biggest scientific controversies of all time, whether what some of these researchers were finding in ALH 84001 were signs of life or not. And as a fairly young scientist, it was really very interesting to go to meetings at JSC and almost see fistfights between people on one side of the fence on this and people on the other. It really got very, very heated. And, you know, I mean, I don't want to say justifiably so, but obviously finding life on Mars is one of the critical questions governing all or finding life in the solar system is almost the critical question governing our exploration of it. Has there been a separate tree of life somewhere else in the universe? If we find it in our solar system, then almost inevitably life is common in the universe. And so we can hope that over the course of our lifetimes, we might get an answer to that, or at least an indication of just how lonely it is. So in the end, there are still people who cling to the idea that there was life in 84001. 99% of the community are agreed that there wasn't. So what we do need to do is let's see what else we can get from Mars. Now, two of the problems with Martian meteorites as sample return, one is we don't know where any of them come from. Now, as a geologist, you really want to know where your rocks come from. Great to have a rock that is, you know, like full of gold and whatever else you might find in Kalgoorlie. Not great if you don't know that it comes from Kalgoorlie. The other problem with Martian meteorites is that none of them are sediments. They're all, almost all of them. There's one that's a little bit weird, but none of them are rocks that come right from the surface of Mars. None of them are rocks that we see with landers and have been able to image from orbiters. None of them are the rocks that are most likely to contain signs of life, and that's a huge problem. We want to be studying things closely that might have life in them. 84001 was an igneous rock. It's not the kind of place that you would ordinarily go to look for signs of life. So a big thing that we want from Perseverance are samples of Martian sediments, because we've never seen anything like that. Oops, bugger, I went past. So this is a Jezero crater in a bunch of different spectral bands, and this is where Perseverance has gone. This is, so what you can see here is actually, it's absolutely beautiful. It's a inflow. It's like a wash from water that poured into the crater and left all of these kind of beautiful. Some of these are contain clay minerals, and almost like you can kind of think about it as kind of a flash flood delta that poured into the crater in a flash flood, probably around about 2 billion years ago, and so that's where, out of many different candidates for where the rover would go, and it was great fun being in some of those conversations around where it would go. Perseverance looked at Jezero looked like being the best spot, and this is the kind of geological map that we can build up from a combination of that crater counting data to get ages, and then things like that spectral data that we get from orbiters to get an indication of the composition. So by making geological maps like this, digital maps like this from all of that digital data, we can then zoom in and think, okay, we want our spacecraft to go to this exact spot and analyze the rocks that went there. And that's why it was a really big deal from a engineering point of view, all of the solutions that those JPL engineers came up with to really narrow down the landing site, because that not only were there places where it was quite dangerous for the rover to be, there were places where the chances of us discovering something are much less. So that's why missions are lovely, because it is this gorgeous back and forth between the scientists and the engineers, and both are stretching each other, both to find new solutions and to see how much we can do within kind of a given technical envelope. Okay, so this is crater again, and hopefully, yeah, lovely. So we can zoom in a little bit. Now, very faintly there, it's not showing up super well on this one. You can see our little red circles. This is another image of Jezero, where we've kind of let crater detection algorithm loose, and it's mapped all the craters down to 20 meters in size. So Mars has a global data set, a global imagery data set called CTX, which I think goes down to like 5-meter resolution, I think, might be 3. And we have now mapped, Gretchen and her team have now mapped the entire planet at that resolution. And they're also going through the high-rise imagery, which has a resolution of between about 30 and 50 centimeters, and are churning through all of that. We have access to that thanks to NASA's planetary data system, where a lot of that imagery is available. So what we've managed to do now is map Jezero at this kind of resolution, which is just awesome. Now here is kind of an idea. It's a little bit difficult to piece together what's happening, but so I'm not going to spend too much time on it, because I want to make sure that we do get to some of the details of Perseverance. But it's basically using that crater count data set to try and develop as high a resolution age map as we can for Mars. So for instance, to give you a feeling, why is that a big deal? If you were able to see that actually in one of those outflow channels, you had slightly younger riverbed than around it, that would be the place to go for your for a rover, or that might be a place you'd want to visit, because it would mean the water has been present there more recently than in other places. So this is just giving a bit of a zoom in on what those craters look like in that area there. It's one of the areas that that NASA are interested in Jezero, and then the age that we get for it is bang on for what, again, people have done in the literature, except it took them an awful lot longer. So now, just to click back to how strange this whole idea of manual counting of craters is. This is currently the gold-plated data set for craters on Mars. There's a dot here for every crater, and they scale a little bit based on size. There's actually 380,000 dots there, representing all of the craters on Mars larger than 1 kilometer. And this guy, Stuart Robbins, did that for his PhD. It took him 5 years to count all those craters. And I would, yes, anyway. So so that was the Robbins data set, and this is what Gretchen has done. And again, on this is what the crater detection algorithm has managed to do. Again, every dot here is a crater. So what it does is it means that then it's really not practical to go much lower than in diameter than 1 kilometer. In Gretchen's data set, we can use the maximum possible imagery data that we have, which means that basically virtually every crater larger than 20-30 meters in diameter, she's been able to count. And that works out at around 95 million craters, compared to 380,000 manually. And that took 24 hours, not 5 years. I'm so proud of that. I think it's just awesome. Just, you know, JPL can't do that. I mean, how cool is that? So this has allowed her and her team to constrain one of those issues that we've not been able to get so far with Martian meteorites, and that is context. So on the left here, I'm not sure if you can see my cursor, is a crater, and then there are rays coming out of it, which are associated with small secondary craters that have been splashed out from that main crater. It's called tooting after because one of the people that first described it came from Tooting in London, and it turns out to be both in the age of the area around it, and the age of the crater itself. So the age of the stuff around it is in red on that plot, and the age of the crater itself is in black. It's an exact match for one class of Martian meteorites, and that's what that looks like. And that's Tooting crater there in the green box that crosses in the one set of ages that we have from these meteorites versus another, and it fits perfectly in that one little spot. It actually turns out that that entire class of meteorites, and we've got dozens of them, it looks like they come from just on the off the edge of Olympus Mons. So it means that we've not sent a rover to Mars, but we know now what the outcrop is for all of these meteorites that we have. Sorry, we have sent a rover to Mars. We've not sent a rover to this spot. And they come from just off the edge of Olympus Mons, and so we're able to analyze them now in the context of understanding the evolution of the biggest volcano in the solar system, which is very, very cool. So we know where one group comes from, which is great, but we still don't have any sediments. So so this is why Perseverance is a really big deal. Obviously, this is what it looks like. This is a very nice little artist's impression. And this was the landing site. And it's a little bit off from where Gretchen's team first did that age, that analysis of the craters there, but they're throwing themselves at that, and they're going to make that data available to the NASA team as soon as they have it. It's not obviously the NASA team will be able to get age data for that exact spot. Gretchen's team will be able to get age data for the entire region around it, which will be really, really beautiful. Now, the what was 2020 and is now Perseverance is really interesting, actually, from a couple of points of view. It's got a very large suite of a payload suite that, in addition to it's doing the sample collection and caching, but it's got a whole bunch of other payloads as well that really pushes much further in terms of being able to detect biosignatures on Mars. So I think really the thing that's special about Perseverance is that more than just about anything else that we have, certainly more than anything else we've ever sent to Mars, it has the capability of actually finding evidence of biology itself. And in the samples it collects, it's really going to if there's no signs of life in the rocks from Jezero, then that'll be a really big deal. That'll be very disappointing for a lot of people that want there to be life in the universe. So a whole bunch of instruments, 7 main instruments on Perseverance. One is the pixel instrument, which is X-ray fluorescence, which gives you really nice elemental composition of Martian surface materials. Dave Flannery, a friend and colleague of mine at QUT, has been working for a long time with JPL on that, and he's on that instrument on Perseverance. Really nice ground penetrating radar, which can detect ice if it's relatively close to the surface, and brines. There's one called MOXIE, which is quite cute, which is an ISRU experiment. So it's actually going to be able to produce a small amount of oxygen. So it's like, this is a step towards us being able to produce fuel on the surfaces of other planets. That's a really big part of Artemis. It's actually the thing that sets Artemis apart from Apollo. We can do, you could do rerun Apollo again, but it'd cost you hundreds of billions if you got to lug all your fuel up the gravity well from Earth. If you can make it on the surface of the moon, then that's a lot better. Obviously, you've got to go into a crater which has 30-degree walls and mine stuff at 30 Kelvin, which is a problem, but you know, there we go. This is a really cool one, SuperCam, which is really a beautiful instrument where you can get chemical composition, mineralogy at a distance and using a couple of lasers and 4 spectrometers. And that's probably one of the most, it's just in terms of detecting biosignatures, I think in terms of what the rover can do in a given amount of time, it's actually a really beautiful instrument. And then also Sherlock, which is another one of these horrible acronyms that NASA likes, which is a Raman spectrometer, which is great for detecting organics. So you have a suite of instruments there, which are really just perfect for detecting life. And I think one of the tremendously exciting things about Perseverance now is that you know, any day we live in a world where that could be the news in the morning. We've never sent an instrument suite to Mars before that is more capable than what's on Perseverance in terms of detecting life. That could be the announcement any day when we wake up in the morning that we've detected life on another world, which is just nuts to live in this time. But finally, obviously the big deal will be trying to bring it back, and that will be the job of a subsequent lander. It's going to be interesting to see how that plays out, depending on what funding looks like for Artemis. Mars sample return is very expensive, and so although at one point in the NASA funding cycle it was really favored, and funding for the moon went down, now it's completely turned around. And so it's great that Perseverance happened. It was kind of in the pipe for a long time. It'll be hopefully both these amazing programs will happen, and we'll get samples back from Mars by the end of the decade. That would be wonderful. Our team has been at Curtin has been involved in every sample return mission of the modern era, and we are certainly well placed, hopefully, to get some of that material to look at when it comes back. So thank you very much. I'm going to stop the sharing there.
Professor Phil, we do have questions from the audience come in. So let me just read out the question that has popped up is, how does the age of the meteorite fragments compare to the age of the lava flows on Olympus Mons?
Yep, that's a really good question. So we've got, what we've got there, there's kind of 2 ways we constrain it with the age. You've got the age of the surface around the crater, and we can count craters on that to constrain that. And we can analyze the age of the rock, and those 2 coincide. And then there's another set of ages that we can get from the rock, which is the cosmic ray exposure ages. And what those date is really, so when the thing is launched into space after another asteroid impact, it's getting bombarded by cosmic radiation, and we get an age. Basically, people that have these incredible instruments called accelerator mass spectrometers can work out basically how long before it arrived on Earth did it get, what was the how far back in time did it get knocked off Mars? In the last 20 million years, it looks like there might have been around about 5 launch events that have sent meteorites from Mars to Earth. Tooting crater is from the craters that the age that we can get from a crater detection algorithm says it's about 1 million years. The age for this type of meteorite, their cosmic ray exposure age, is 1 million years. So you've got those 2 matches. You've got the kind of background age for the region and the crystallization age for the rock, and you've got the correspondence between the launch crater the cosmic ray exposure ages of the meteorites. I hope that makes sense.
It does make a lot of sense. We do have a next questions. Has the software been used to count craters on the moon?
It has, and that's working really, really well. It's really interesting. So we've started out by looking at the Apollo landing sites, and then we're also looking at the Chang'e 5 landing site, where the Chinese sample return mission happened, which was successful in December last year. But then we're just going to throw it at basically all of the moon, and especially like the Lunar Reconnaissance Orbiter camera data set, and do the same kind of just massive data set for the moon. And there's an awful lot we can get out of that. It'll be able to tell us, we still don't really know how long the moon was volcanically active for, where like recent, lava flows might be, or lava tubes, or where, igneous activity was. You can often get ore deposits. So there's an awful lot we can get out of basically just what's lovely is with Gretchen's team can essentially generate and from all that digital data, an age map for an entire planet at maximum resolution. It's beautiful. So they're doing that now. They're also doing Mercury, I think, as well.
Thanks a lot. Does anybody else have any other questions which they want to ask? No, we don't have any questions coming in from the audience. I believe we are small enough to open up the mics if anyone else has a question.
So I have one for Phil, if I may.
Yeah, sure, go ahead.
So money aside, if you could define and design your mission to Mars, what would it be?
That's a nice one. I can do, I think, well, I mean, humans, obviously, right? But someone did work out actually that in terms of value for money, in terms of like, numbers of papers, citations, scientific discovery, Apollo is actually about the best value mission that there has ever been. It's kind of crazy, and that a single geologist on Mars with a geological hammer would be able to do more than all of the missions since Viking, which is kind of cute.
Good answer. I will reuse that.
You can use that. But there's so much we can do, I think, at Mars. In just really, really cute ways. And I think, like going back to Colin's idea for Beagle and trace methane, people have tried to do that from orbit, and that's great. But I think more gas analyzers like that on all landers would be really, really cute. And so a thing that we've been doing is really trying to kind of miniaturize the what was on Curiosity. So Curiosity had a methane detector on it. Really, it's a cute one, which we're basically trying to get that into a CubeSat form factor. So you've got an instrument there that could go on other landers. It's also kind of a fun one because it means you get like super sensitive for things like, put a methane detector on a drone and sniff things for oil and gas companies. Yeah. So we're playing around with things like that. But I think it's basically trying to think of shortcuts to places that might have life on Mars. I think there's still a lot of opportunities for that. Mars is interesting because it's kind of been, sorry, I'm rambling now, is that because, the US didn't go back to the moon for until Clementine. I think that's right. And then since then, it's not been part, they had a real fully organized program of exploration for Mars, and culminating, now with the potential to bring back samples. And so in terms of, orbiter data, it's pretty much been, I don't want to say it's been done. You can always improve it, but I think it's in landers. It's in novel experiments for landers. It's in thinking about how you get to, how you get a cute little package to a difficult to reach place. It's that kind of stuff. So I think you can do interesting things at Mars, without breaking the budget, obviously working with international partners. Yeah.
Thanks for that. I like this return mission and the fact that there is so many agencies working together to make it happen. That's what's wonderful about it too.
Yeah.
Thanks.
Thanks a lot. That was a really great question and a really great answer. I also have a question which clouded my mind as Aude asked the question as well. How do you consider the craters on Earth, Moon, and Mars? And how do you determine what's best as a landing site from the data you get from the photos or the radar imagery?
Yeah. So do you mean how do you, like, for Mars? How do we determine a landing site, or?
Yep. So just looking at Earth as well, you will have data for Earth craters, and then you will have data for Moon craters. Yes. How would be the accuracy of, because it's still, again, it's an image as well. Earth would be more reliable, but then Mars might have some roughness coming in the data.
Absolutely, no, exactly, that's right. And so obviously, you probably know, Nimesh, a huge big deal with any machine learning approach to image recognition is your training data set. And so Gretchen's team spent an awful lot of time on that, and then validating that, and they got battered trying to get, because you've essentially got an entire generation of planetary scientists who spend their lives counting craters, who really, aren't too chuffed about the discovery that actually you can do all of that in 24 hours. So she did have to jump through some incredible hoops there. In terms of selecting a landing site, after you've done this, it was beautiful, actually. They had this whole kind of sort of multi-parameter assessment, and then it was kind of a whole bunch of planetary scientists who were voting for different locations and arguing over different locations. It was a really kind of inclusive process. That was really interesting to look at that, to see that.
Thank you. That was a really good answer. I think we have finished our time for today. Does anybody else have any last questions before we close out the session? No? Okay. Thanks a lot to Aude and Professor Phil for coming out and sharing such insights about the space agency, and as well as the Perseverance landing and the geology behind it. That was a very good learning curve for members. So this will be available online on YouTube as well, to both Adelaide and Sydney section members as well, for those who couldn't make it today. And thanks a lot for your time today. And we will send you a gift back for taking the time out. And we will reach out to you and send you a cool gift back. We do it with all our speakers. So most of our speakers have a Aussie traditional gift back, which they receive.
We're curious now. Thank you for having us anytime. Really, it's good to be able to talk about this, and thank you, Phil, for accompanying me today, because that was really awesome.
Lovely to see you again. Lovely to see you again, sweetheart. Look forward to catching up soon.
Thank you very much, everybody.
Bye, guys.
Thanks.
Take care. Bye-bye. Bye-bye.